It's a great pleasure for me to introduce the last speaker of today and of this workshop, who's Dimitri Wyss from Lausanne. And he's going to talk about Donaldson-Thomas invariants from non-Archimedean integrals. So Dimitri, you can go ahead. The floor is all yours.
Thank you so much for the invitation. And thanks to the organizer for putting this together over so many weeks. It seems even more tiring than doing an actual conference. It just lasts 1 week. And so since I'm the last the speaker of this, I think I should also we should also try to thank at this point the organizers for putting this together collectively in these strange times. Every effort for the community should be even more valued than usually. So thank you so much for organizing this nice series of talks, everyone. And then I will start with my talk. So it will be about Donaldson-Thomas invariants and how to get them from non-Archimedean integrals. And this is joint work with Francesca, Carocci, and Giulio Orecchia, who we already heard right at the end of the last talk. So very involved in this. And so it's a bit similar, but I don't want to say much about what David knows or doesn't know. Anyway, I am not a huge expert in this Donaldson-Thomas invariants, but it's also part of enumerative geometry, and I sort of come also a bit from outside with these non-Archimedean ideas. So it seems sort of at least morally a bit parallel to the previous talk that we just saw. So the rough idea, let me say it like this. So if you want to count some curves in an algebraic variety, so this is very the x say very generally over the complex numbers, then usually one does is one constructs some moduli space of well, you would say curves, but that's maybe not so easy. So sometimes you think of curves as maybe ideal sheaves, and then we can construct some moduli spaces of sheaves, or maybe it's also some moduli spaces of maps from curves into your space, in some sense, and you get some space, say just M of X, and then one considers some sort of let me say some Euler-characteristic. Say, just write like this. So Euler characteristic of your space, and this will give you some integer, and then this you call the sometimes virtual count of say curves in your space. And if in the ideal case your moduli space were just some finite number of points, and these were the number of curves you were actually counting. And then in general there is always some geometric pathologies. Your space is not smooth, and so on, and you have to do more than just taking Euler characteristics. And in the case of these DT invariants, so I'm not going to define actually these invariants. I'm sort of going to define them, but I'm not really. I don't want to talk that much about them. But let me just say, in the case of these DT invariants, what one actually considers is the Euler characteristic of basically the cohomology of your space, but not just not with, say, constant coefficients, but where you have this coefficient system phi, with phi a certain perverse sheaf. And a perverse sheaf, you can really think of it just being a local system. Typically will be maybe a complex, but in a first approximation, it's just some local system. And this will, so you have to define the right moduli space and then define the right perverse sheaf. And then you cook up this DT invariants. And the goal of this talk is to describe another way maybe let me say in some special case. I cannot speak in full generality. Actually, it's the way I presented it's a rather special case, but I hope it can be extended in the future. So another way to obtain this, so let me call this maybe star. To aim this star. And in fact, so this is an Euler characteristic. So we obtain a sort of motivic refinement of this. Without actually using actually neither any sort of cohomology nor this perverse sheaf phi. That's why I will not go into much detail about what it is, but instead we'll use, so another way without using, but instead with what we call non-Archimedean integration. On this moduli space M of X. And so if you're, of course, depending on your background, but this is, after all, seminar on non-Archimedean geometry. So this, you should like this a lot. So we have kind of involved construction of this perverse sheaf, some cohomology theory, and then we take sort of cohomology groups and its Euler characteristic, and it's maybe a bit it's kind of heavy technology to carry around, and instead we can sort of with a rather simple, from our point of view, tool reconstruct these numbers or these invariants from completely different from a completely different geometry. And so this is, I think, both interesting for these DT invariants, but actually also for just non-Archimedean geometry of these moduli spaces themselves, since they seem to be related to some cohomological data, and we don't think we really know why or how. And so now let me start being a little bit more precise and explain the setup, or the in which we prove something. So for this, I fix a smooth del Pezzo surface. So again, for now, just over the complex numbers, and then to construct the moduli space, I need some numerical data, basically. So I take an ample curve class. And chi some integer, and then I defined a certain moduli stack. So let me call it like this. So this stack will depend on beta and chi. Actually, for the whole talk, the beta, this curve class will be fixed. And so I will just write m of chi, and it is the stack which parameterizes one-dimensional semi-stable sheaves F on this surface, satisfying the following two properties. First, so since the sheaf is one-dimensional, if I look at its support, I should get a curve class, and I want this to be the class beta that I fixed. And I also want that the Euler characteristic of my sheaf is this integer chi that I fixed. And basically, the main reason why we consider only the Pezzo surfaces is the following. So in this case, it is some deformation argument to say that m chi is actually smooth, or let's say non-singular as a stack. And so that is very convenient. And so before, when I wrote this straight m, this was actually the moduli space. So this is the stack of sort of all semi-stable sheaves. But then we can also using GIT, we can construct an actual algebraic variety. And this will also be important. So let me introduce it. So we have m chi to m chi be a coarse moduli space. And the last geometric gadget is this map, which goes from the coarse moduli, or I mean, you can also construct it from the stack to the linear system associated to this curve class. That's just some projective space. And it sends a sheaf to its support. And this is called, so we call this H chi. It's called the Hilbert-Chow morphism. So, and maybe I finish the sentence, and this, the Hilbert-Chow. Map. Like this. Okay. So again, so this might seem a bit obscure. What is the geometry of these things? So let me say two properties which sort of I don't know, clarify a bit what's going on. So over a smooth curve, so these are all the curves sort of linear equivalent to this beta. So over a smooth curve C inside this this base B, the fiber of the Hilbert-Chow morphism will actually just, so the sheaf, so this will be sheaves supported on this smooth curve, and these will just be line bundles. So these are line bundles on C of a certain degree. The degree is chi minus 1 plus the genus of the curve of C. So we have, so is some generically is fibered in Picard varieties of a certain degree, and then as you degenerate to singular curves, it becomes more like a compactified Jacobian of some degree or something like this. So very similar to Higgs bundles in that sense, and to the Hitchin fibration in this case. And so if this, furthermore, so if this pair of beta and chi is generic, this means that every semi-stable sheaf is actually stable. So you have this equivalence. Then M chi, the moduli space M chi is actually smooth. The stack is always smooth. The space is smooth if we have sort of a generic choice of beta and chi. So this happens, for example, so you can always achieve this by taking chi equal to 1, if you like. Then you will always have this property, but in general you don't. And so sort of for this talk, what is really interesting is the case then is smooth. But in general, this M chi is singular in general. And yes.
Can you describe which compactified Jacobian you get?
What do you mean by which?
Oh, they're classified. Yeah, they're classified usually. Some choice of stability condition.
I mean, this is sort of, yeah, so it's, how do you call it? It's called like Simpson's compactified Jacobian. And I mean, it's sort of given by the, so I haven't said, but you should fix a priori polarization on S, and then this will, I will fix one for the curve. And so it's the compactified Jacobian for this polarization.
So roughly, if you go to the singular curves, you're just adding.
I cannot really hear you. Sorry.
Can you hear me now?
Yes, more or less, yes.
So you're saying that if you go to the singular fibers, you're adding, I mean, you don't have line bundles, but you have rank 1 sheaves.
That's right.
That's it, torsion-free rank 1 sheaves.
Yes.
Right, okay.
Yeah. But I mean, then you get, I mean, it depends, right? So basically, if your curve is integral, then there's still sort of only one possible compactified Jacobian. And then if your curve kind of becomes
Has many components?
Yeah, then you have to choose. I mean, then the polarization you chose will probably tell you which one it is. But I mean, I mean, you will just have semi-stable sheaves, one-dimensional sheaves with support on this thing, on this non-reduced curve, non-integral curve. And I think that's what people call Simpson's compactified Jacobian. Okay, more questions? Okay, so this M chi is singular in general, and that is the case we're really interested in which case actually sort of also in the cohomological sense, this perverse sheath shows up and things become difficult. So and so in this case, M chi, it comes as I said, with a perverse sheaf, phi of chi, which encodes the DT, this curve counting invariance. Of the surface and this numerical data. So now in this case, it's kind of special. In this Del Pezzo case, one can actually say what this sheaf is, this perverse sheaf. It's maybe the only at least the only perverse sheaf, more or less, that I know, which is the intersection complex of the singular variety. And this is a result to Meinhardt. So it's kind of explicit, but it's kind of known that this is not always the case. If you go beyond this Del Pezzo case, you will not have this this description as IC sheaf. And also somehow it's not for what we do today. It's really not relevant. This form of the sheaf. Somehow what is relevant is the following theorem, which is due to Maulik and Shen. Kind of a recent result, which says so. Originally, they assumed that S is toric, but I think they basically assume. So let me write it in brackets. S is toric. They assume this for some dimension estimates, and they can only prove in the case when S is toric, and then they mention if you could prove them otherwise, then this is then the result extends. And then very recently, I think a couple of weeks ago, there was a paper on the archive which seems to prove this dimension estimate. So now I think this will hold for all Del Pezzo surfaces. So that for any chi and chi prime in Z, we have isomorphisms between so there's sort of a global statement which says that the intersection cohomology for M chi as a sort of graded vector space and M chi prime, so that's intersection cohomology, of these possibly singular varieties, they're isomorphic together with extra maybe Hodge structure and other structures you might want to have. But in fact, they show more. They show a refined statement about sheaves. So not only on the cohomology, but already on the level of complexes, that if you take the push forward under the Hilbert-Chow map of this IC sheaf, or maybe I should, so it's the IC, but actually, well, no, it's really the IC of M chi, then this is already isomorphic as a complex of sheaves to ICM chi prime as sheaves on the base B of the Hilbert-Chow. And so if you push down further to the point, you get the first statement. Okay, it's a very nice theorem. So where does this come from? So the point is that this proves a conjecture of Toda, which fits in sort of a general framework for curve counting on Calabi-Yau threefolds. And so here the threefold you should consider. So we're here on a surface, but then typically the way you get from a surface to a threefold is by looking at the total space of, in this case, the canonical bundle of your surface. That's your threefold. And you can sort of go in between these two theories. And this conjecture is sort of related to the relation between Donaldson-Thomas and Gromov-Witten invariants. And so it's very, very natural to expect that this is true, but it sort of also characterizes, at least over the base B, this DT invariance in the following way. And now we get we leave a bit the world of complex geometry, and we do something that we actually then can translate into the non-Archimedean world. So So this theorem will imply will imply the following, or like implies the following reformulation. So we now choose spreading out and then we can consider everything, and by everything I really mean your surface, your moduli space, this phi or the intersection complex, essentially with the same geometric properties, but now living over some a priori very large finite field. Okay, a field with q elements. Okay, so just take all the equations somehow that are involved in defining all these things, and you reduce them modulo some. I mean, you consider them in some big finite field, and what you then get is so there over a finite field has this function sheaf dictionary. So if you have a first of all you have the trace formula, so counting points is like taking the trace of Frobenius on the L-adic homology. And furthermore, you have some local system, or in this case, a perverse sheaf. You can also look at the trace of Frobenius acting on fibers of this. And this will give you some function. And it's sort of like, so it will give you some additive invariant of your sheaf. And so that's the function we get here. So we look at k rational, so finite field rational points of your moduli space. And we get a map to QL bar, but just this is isomorphic to the complex numbers. And it sends a rational point to the some normalizing factor, just q to the minus dimension. And then so we take the trace of Frobenius on the fiber of this sheaf. And when you have this, then now the theorem, so by spreading out, you can actually spread out in a way that also the theorem holds. The theorem then implies the following. First, of course, if beta and chi are generic, then this DT function, well, then if it's generic, then this this perverse sheaf, well, it was the intersection homology, the intersection complex, but this in this case is just the constant sheaf, and so you get simply the constant function, which is just a normalization. So each point is, I mean, you're just counting points, but for each point, then you count one. And so in this case, as I said, there's not much interesting. And the interesting part is really if you have chi and chi prime in Z and B some point in the base. And then, so the statement that the push forwards, so this was the statement here, that the push forward of the IC complexes are isomorphic. Well, it will tell you for this function that if you sum up the value of this function over a fiber, so you have some B in the base and you sum up everything over the fiber, over all k rational points in the fiber here, then this has to be the same as the sum over, say, y over the fiber on the other side.
Excuse me, Dimitri.
Yes.
You are now working with this modular space and positive characteristic, which puzzles me a little bit. Do you take semi-stable or strongly semi-stable sheaves here?
What do you mean by strongly?
Yeah, usually you have problems with these modular spaces when you have semi-stability, which is destroyed by Frobenius. So often people work with strongly semi-stable. This means
strong.
Yeah, this means Frobenius doesn't kill it.
No, but here it's really, I mean, this can probably only happen if the characteristic is sort of bad with respect to some numerical data from your sheaf. And here it's really like check a huge finite field, which avoids all these problems. So
okay.
Yeah. So really, I mean, it's really through so we spread out the surface, the base surface, but actually if you choose the field big enough, then it's all actually the whole modular space is just spread out.
Okay, thanks.
Yeah, so there's none of this. So maybe one should, so since the field is not algebraically closed, someone has to, for example, talk about geometrically stable instead of stable. So this sometimes, that's right. So Francesca just wrote what I said. Yeah, so no, there is no issues here. Okay, so you have these two properties, and so some of the point of view is that sort of these two properties determine very much this DT function, because in the smooth case you exactly know what you do, you just count points, and in the singular case you don't know, but you at least if you sum up over a fiber you can compare it to the smooth case. For example, if you take chi prime equals to 1, you will be in the smooth case, and then it also tells you what happens on the singular case. And now, so next, we'll construct a function which I call P for p-adic, or yeah, somehow prime. So this p-adic DT function satisfying also these properties 1 and 2, using so we construct this function satisfying 1 and 2, and in fact, as a spoiler, and we expect in fact that this p dt of chi equals so you can compare it once you sum up over the fibers over the base, but in fact we expect that we really get the same function for all chi. This we cannot prove yet. At least we can construct it and prove 1 and 2. It's very natural to expect that this holds. And so I said this now many times and it was in the title, so maybe I should explain what I mean by this non-Archimedean integration. So now we get into more familiar territory. So I let F be a non-Archimedean local field. So this could be a finite extension of QP or FPT. And so then I have O, I will note by O inside F the ring of integers. And K, which will be again isomorphic to FQ, the residue field. And furthermore, we also fix a Haar measure. We call it mu, such that the mu of the ring of integers equals 1. And so with this data, we can then talk about integration on algebraic varieties over O. So let X be a smooth algebraic variety over O. So that means it's just some finite type scheme with a smooth map to O, separated. That's what we need, and maybe it should have a smooth algebraic to O. It should not have components with different dimensions. Otherwise, it's a bit funny. So let me fix some relative dimension D. And then what you can consider are the O points, the O rational points of your variety X. And also so because this is a variety, it's supposed to be separated. If you restrict the map from spec O to X in here to just a map from spec F to X, this will be an inclusion, and you get this inclusion into the F rational points of X, and these are both what one can call an analytic manifolds. Manifolds, let me say in a naive sense. So it's really the rational points, and simply because the variety was smooth, the equations that define them are smooth, and so by the inverse function theorem, the locally will be covered by analytic charts, and then you get analytic manifolds. But it's not like a Berkovich space or anything. So these will be topological spaces. They're totally disconnected, and they're sort of the things people usually try to, I don't know, it feels like people usually try to avoid them and modify them. But for me, for now, they have worked just fine. So what is also interesting, so this compact guy, the O points, is what we will care about. And so you have this restriction map, which just mods out by the maximal ideal in your ring, and you get from an O point to a K point. And again, this map is actually surjective because we have Hensel's lemma. So if you have a K rational point, then I can always lift it to an O rational point because X was supposed to be smooth. Okay, and so how to think of this? So as I said, it's a sort of naive thing, but that doesn't sound so promising. So maybe a better way to think is that one can think of X of O as a sort of as a shadow of the arc space. Of X. So recall that O could be, for example, something like O could be like FQ double bracket T in the École-characteristic case. And so this is, and then it's really somehow the FQ rational points of the arc space of your variety X you started with, but we remember much less. So we don't remember the scheme structure, just this sort of rational points together with the analytic topology. But now this sounds more promising because at least if X will become singular, we know that the arc space is it's a very interesting but also intricate object, and then sometimes it's good to forget some aspects of it. And this is not the only thing. Remember, so there's a nice gadget, which is why we call this whole theory integration is, so Weyl observed that X of O, so this smooth manifold, analytic manifold, admits a canonical measure. So a Borel measure, which I can define right here. I think it's a very neat construction. So you just choose any gauge form. So gauge form means non-vanishing, and so it's a D form, so same D as the dimension of X, and it doesn't vanish, or sometimes called a volume form. So any such form on omega I on an open cover of X. Ui, I. So X might not have a global form. That would mean that X is Calabi-Yau, but at least locally one can do this. And then you just notice that the absolute value of omega I and the absolute value of omega j are the same on intersections, since units in O have absolute value 1. Absolute value equal to 1. And then, so this I haven't really explained, but in this naive analytic setting, you also can define integration, but you cannot actually integrate p-adic functions or f-valued functions, because the Haar measure does not take values in f, but only the real numbers. So you can integrate sort of real valued functions. And in particular, you cannot integrate omega I, but you can integrate the absolute value of omega I. And then integrating omega I on ui of O, so the O points of this open cover, this then glues, because on intersections, these absolute values agree. So this glues to a measure. Which I will call the canonical measure, because it doesn't depend on anything on X of O. And then the theorem that comes with it is that it sort of describes this measure because it's canonical. So it should be describable in terms of just X. And it has this very nice form. It tells you that if we just compute the volume of this analytic manifold, it gives you the number of points of X divided by Q to the dimension. And here's the number of points in the finite residue field. And in fact, it's not very difficult. For all X rational points, you have that the canonical measure of the inverse image of a ball is exactly 1 over Q to the dimension of your variety. This is just basically this ball is just like the maximum is isomorphic to the maximal ideal to the power D, and this is a simple computation to compute this volume. So far so good, a canonical measure, and we can count points with it. And so what we gain, and this is sort of this funny little magic, is that now on the left-hand side, so on this analytic side, we're a bit more flexible that just on the discrete set that we're counting on the right-hand side. So this very simple observation is kind of crucial, so that if you have Y in X strictly contained closed subvariety, then the dimension of these O points of Y will strictly be smaller as an analytic manifold, the dimension of the O points of X. That's in this case. So for all these analytic things, you can just think of as like the real numbers, the theory, except that you don't have this O for the real numbers, but otherwise it's just the same. So this dimension is the same, works the same. And so if you integrate, or if you compute the canonical volume of these O points, but with the canonical measure on X, you will get 0 because you're integrating a D form on something which is of dimension less than D. And so you can actually remove some, on the left-hand side, you can remove some small sets of arcs in your space without actually changing the volume. And this gives you a little flexibility, and with something you could not see on the finite field level. You cannot remove any points. So that's the smooth case, but I just said the smooth case is not so interesting. And so now the point is that even if X is singular, one can sometimes construct canonical measures. Meaning they don't really depend on any choice. They just depend, I mean, they depend on the geometry of X, and in this case on the singularities that come with X. And so the sort of known case was when X has quotient singularities. Or maybe more general, X can be Q Gornstein. And I think in this sense, this sort of appeared in works of Denef and Leuser for motivic integration. And they had quite a few applications. So originally, this gave some sort of Mackay correspondence for actions of finite groups on A2. And then we also used this to prove some statement about cohomology of moduli spaces of Higgs bundles and related objects. And so it's already quite interesting. And now we can have another case when we can do this. So, and this is the case when X is similar, but so quotient singularity means you're a quotient of something smooth by a finite group. And so you can see X as some sort of coarse moduli space of the Lean-Mumford stack. And now we can sort of extend this to X when X is a good moduli space. Of a smooth. In fact, I mean, there's various variations, but for today, let's just say a smooth Artin stack. So that's exactly, for example, the case for this M chi, the stack was always smooth. And so in general, we have some smooth Artin stack chi and the map to its good moduli space. And then we have some extra assumptions. If X is modulus of a smooth Artin stack, then under some extra assumptions, integrating. So I'm not going to say all the assumptions, but now just what I will write now are already some assumptions. Then basically integrating any gauge form. But I want to say it's sort of similar than the Weyl measure we saw before. Omega on I call this stabilizer free. So this stack, you can think of this stack as being something like M mod G, where M is a variety and G is a group. And then the stabilizer free locus will be sort of the locus where G acts freely on M. So on this stabilizer free locus U, so of course you have to assume that this exists. So that's one of the assumptions. And then this will induce a measure. Which I do, again denote by mu canonical on, but not on the stack, but I really want it on the space. So on X of O, and maybe you have to restrict to so points in O which generically lie in the image of this U. This stabilizer free locus. And so for this measure to be non-singular, you should somehow have this U, I mean, should sort of be mapped isomorphically to its image. But otherwise you just get the trivial measure. Oh no, and so again, so why do I call it canonical? Measure on here, which will be independent of the choice of the gauge form, or again, maybe local gauge forms. And so this is the first result, or one of the results we prove in our paper. And I think this on its own is already kind of interesting. So now there's lots of new singular spaces. We can try to compute these volumes. And so this, I think, is should be very interesting. It should be interesting. To study this measure for other so what I will do now, I will tell you what this measure should do in the case of these moduli spaces of curve of sheaves. But you can take, there's many other Artin stacks which have singular good moduli spaces. And for example, actually where I saw this first was in a paper of Satriano and Usatine, where they particularly look at the toric case. So every toric variety is somehow the coarse moduli space of a, I think what they call a Fanta stack. And then there they look at integration there. And there should be many more. Anyway, so then with this measure at hand, so now in our case, we then define, so now again we have to sort of spread out and everything will live nicely over this ring of integer. Again, if you choose the characteristics big enough, this will actually, so if S, the surface you start with, you make it smooth over this ring of integers, then everything moves nicely to over O. And then we simply define, but now so now this M chi will be singular, and this measure will be sort of capturing interesting information about the singularity. And essentially, what I would like to write is that I now define this DT function. But so X, recall, is a point over the residue field. And this function, I define it in terms of arcs, which restrict to this fixed point in the residue field. So R was this restriction map, the subset of the arc space, or this shadow of the arc space. And I would just like to integrate the volume of this ball around this little point X, which I can almost do, but there is some correction function, which I just denote by f of chi. For now, I think I'm running a bit out of time, so maybe I cannot say so much about this function for some. So this will be some natural function on this space. Complex numbers. Maybe I will say two words about the proof, and then we'll see why this function has to be there, and does this. And then with this definition, we indeed have so theorem. So again, this will be the three of us who prove that this PDT satisfies 1 and 2. So maybe, okay, I do something which we shouldn't do, but I scroll up to recall what is 1 and 2 are. So the first one, so now we should think of, can I have some more pointer? Yeah. So the first one was that, no, this doesn't work. Okay, I tried. So the first one was that if beta and chi are generic, so if the space is smooth, then this PDT should just be sort of Q2 minus the dimension of X. And this will just be, because in this case, this canonical measure is this Weyl measure. And we said that then the volume around each point is just 1 over Q to the dimension. And the second one is really sort of the whole point of this story, that we can sort of we can compare these integrals for different Euler characteristics, right? And so I have 3 more minutes, so let me maybe say a few words why this is true. So it satisfies 1 and 2. So let me say proof. So 1 was follows essentially from Weyl's theorem, and 2 is again some sort of a Fubini statement. Fubini argument by integrating over the fibers of this Hilbert-Chow morphism H chi and H chi prime respectively. And so it reduces and so here's the whole magic of the thing, that as I said, the fibers of this Hilbert-Chow morphism are generically very easy. They're just Picard varieties. And then you degenerate and become sort of hairy. And then so they become compactified Jacobians. And then there were some questions, and maybe it's not even clear always what it means to be a compactified Jacobian and so on. And so here, this somehow, we don't have to worry about anything of this. So it reduces to show for any B in the base space, but also we can assume by this measure 0 story that generically this B lies in the smooth locus. So that's the smooth locus means where so remember B was the linear system, and I want this F point to represent a smooth curve over F, which is maybe singular over O, but generically smooth. And then you need to show something like, if you integrate over pic, so say so C is my universal curve over the linear system, then I would like pick C of B, and here I have some degree D. I have this function, so this D, sorry, here you should have chi plus G minus 1. And then here you have F chi, and you need to compare this to some other pic, where you have here chi prime plus G minus 1 of CB of F chi prime. And during and so here you have to integrate over F points. But now these spaces are very similar. These two pic spaces, in fact, if they have rational points on both sides, they're just isomorphic to pick 0. And if not, then they will not be isomorphic. But then actually one will be empty. And then the function, so this f chi, it's the last thing I'm going to say, f chi and f chi prime make this integral vanish if the other side has no rational points. So it's sort of an arithmetic, so very nice, subtle arithmetic argument that comes into play here. And yeah, I think I stop here. I wanted to say thank you.
Let us thank Dimitri for his talk.